Alrighty, good morning, gang. Welcome back. Today is our last class meeting before exam 2. So we are going to spend the majority of the day today doing whatever it is you guys want to do. I'm happy to work any problems you guys want to see worked out. I don't mind working homework problems, study guide problems. I can modify them a little bit and work them. That's okay. If there's a particular part of a study guide problem that you're really stuck on, I don't mind working it. Just be mindful that I do want to see your effort on the study guide. So if you're going to annotate or add stuff to the study guide based on what I show you here today, just make a note of that came from lecture. I think it is better for me to see what you do on your own so I can give you some feedback on that than me to see my own work just reproduced on the page there. That's not super helpful. So I'm going to start here by kind of introducing a little bit where we're going. We'll talk about that just for a second. And while I do that, I would like for you guys to, in the chat, tell me what sort of problems you want to see. They can be a specific homework problem, like homework 10, problem 15, or it could be a general question, like how do we do this thing, or how do we do that thing, or what, stuff like that. Just let me know whatever it is you guys want to see today as a part of your review. Alrighty. So while you guys are filling the chat with lots of good things for us to work on, I will flip over to the document camera here and just start to explain a little bit where it is we're going. So after the test, we will be entering. Sorry, don't know how I muted myself. I must have hit a hotkey on accident. After the test, we will be going into a totally new place. So of course, this is MAC2311, section OH1, which is a Calc 1 honors class. And today is the 1st of November, 2021. And if you are here in Gainesville, the weather is just beautiful. Lovely and chilly, and it's a perfect fall Florida day. And we don't often get those. Today we're doing two main things. We're going to preview the 3rd unit of the course. And then we're going to review for exam 2. And exam 2, remember, is Wednesday. That's our next class. Okay. So again, the thing to do for the review, please just type into the chat the problems or problem types that you want to see discussed. You can say graphing or L'Hopital's rule or implicit differentiation or related rates, or you can tell me a specific problem number from the study guide or from the homework. All right. So far, everything we've done relates to tangent lines. And the derivative. In some fashion, right? Limits can kind of be thought of as their own thing, but really we started talking about limits so that we could introduce the derivative. Tangent lines, that geometric object, the tangent line, is its own thing, but it has to do with rates of change, which are the derivative again. So everything we've done so far is called differential calculus. Calculus having to do with differentiation and the derivative. The last part of this class, the last third of this class, I should say just third, 1/3 of the class, is about something called integral calculus, which is primarily concerned with, I would say, kind of like tangent lines and the derivative. I would say here areas and antiderivatives. And areas are kind of the place to get started. So a classic question is, can you find the area under the curve y equals x squared on the interval (0 to 1). Mark this as 1 here. It's a pretty silly scale, I know. Mark this as 1. Of course, this parabola is symmetric. It's got stuff over here. But really, I'm looking for yeah, here. Looking for this area. Or more generally, can you find the area under any curve, right? But the blue area here is kind of like the tangent line for integral calculus. It's like the main geometric thing that we go trying to find. And then, of course, we can go all sorts of different places, right? Nobody would have guessed that tangent lines will lead us to something like related rates. And in that same fashion, nobody would guess that looking for the area under x squared from 0 to 1 would lead us to infinite series or power series or any of the other beautiful places it does lead us. But in that way, that math kind of grows and branches from one place to the next. The integral calculus will grow and branch from this very simple area problem into a much deeper and full, rich field of mathematics. I don't want to get into the details of how we find this area, beyond saying that eventually we will connect it to something called an antiderivative, which is what it sounds like. It's like a backwards derivative. And that connection is provided by a famous theorem called the fundamental theorem of calculus. What I do want to talk about here today, what I do want to show you and discuss a little bit, is a couple of different ways that brilliant mathematicians have approached this problem. One of them, somehow everybody comes up with on their own, and the other one was thought up by Henri Lebesgue, a Frenchman, Henry, if you like in English, in 1901. The others were thought of by Newton, Leibniz, and a bunch of other people going back a long, long ways. In fact, the basic area problem was solved by the ancient Greeks. I don't believe they knew this exact area, but some other areas bounded by curvy things were figured out by the ancient Greeks. For example, the area of a circle, they knew. This area happens to be 1/3. And it's going to take me a lot of work to convince you that that area is actually 1/3. It's, it's not a triangle because it's curvy on this side. And the fact that it's curvy on one side makes finding the area really challenging. You can't like split it up into things that are geometrically very simple unless you use a shitload, and by shitload I mean infinitely many things. So kind of two main approaches to this problem. And we will stick with one of them. Both involve rectangles. And if you go on to take more advanced types of calculus classes like real analysis, or advanced calc is the name of such a course. If you mention the second one, when your calc professor, your advanced calc or real analysis professor gets to it, they'll be very impressed. You can use vertical rectangles. And this is where you take the area and you chop it up as best you can into rectangles that are oriented top to bottom. So, I can draw in a rectangle like this, and 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 a rectangle like this. Now, clearly the area of the rectangles here is too big. It's too big, right? It's more than the area under the curve. I could have drawn this in a way that the rectangles would be too small if I let their height be determined by the value of the function at the left end point. But vertical rectangles is one way to do it. And shade the area here. All right, clearly this is too much. The actual area is the blue shaded area, and the area of the rectangles is more than I want. But if I use many very, very narrow rectangles, this gets better. This gets better with more and narrower rectangles. And what you'll see is that in the end, we'll use a certain limit that will send the number of rectangles to infinity, their width down to 0, and you'll get the exact area. And that will be the approach that we take. The other approach, and so people came up with this shit many hundreds of years ago, right? The first person to do it formally would have been Riemann, but Newton and Leibniz certainly had some idea of this back in their era as well, in the 16th century. For some reason, it took like 500 years for anybody to go, hey, what about horizontal rectangles? And that man was Henri Lebesgue. And the type of integral that you get out is what's called a Lebesgue integral. So again, I'm looking at the interval from 0 to 1. And instead of using horizontal rectangles, nobody can stop me from coming in here and saying, let's do, sorry, instead of using vertical rectangles, nobody can stop me from coming in here and saying, let's do the horizontal ones instead.
How do you spell his name?
So this was formalized. This is like the vertical rectangle stuff is like Newton, Leibniz, and then finally formalized by a guy named Riemann, also Darboux. The modern formulation is called the Darboux integral. The version we're going to study is called the Riemann integral. The Darboux integral requires a notion of supremum and infimum, which we don't have. The horizontal rectangle, this is Henri Lebesgue. The Frenchman, so it's like Lebesgue, but Lebesgue is how it's pronounced. And the integral that you get out, the sort of calculus operator that you get out from this is called the Lebesgue integral. The operator you get out of this is usually called the Riemann integral, but in an advanced calculus class, you call it a Darboux integral. There are advantages and disadvantages to each. The advantage to the Riemann approach is that the heights here all come from values of the function, and you're chopping up the domain. So you chop up your domain into little pieces, and then on each of those little pieces, you approximate the area by a constant function, by a rectangle, which is like a constant function. In the Lebesgue picture, you chop up the range. That's really what you're doing here. And then you approximate your function uniformly, I might add, by what are called simple functions, functions that are constant, again, right? That's the idea. Each one of these rectangles is the area under a constant function. But you get there by chopping up the range first and drawing your rectangles horizontally rather than chopping up your domain and drawing them vertically. It turns out that the Lebesgue approach is much more powerful. These both get better with more rectangles, right? The advantage to the Lebesgue approach is that your function doesn't really need to be nice. See this, the Riemann integral, the vertical rectangle approach kind of requires that your function, well, let's say continuous for now, right? Turns out it's a slightly weaker criterion called integrable. But certainly this works well for continuous functions. But if your function is badly discontinuous, this doesn't work well. This works well, even if your function is brutally discontinuous. Do you guys remember at the beginning of the semester, I talked to you about the Dirichlet function, the function that spits out 1 on the rationals and 0 on the irrationals?
Yeah, it made the super cool pattern.
Yeah, it was really, really weird. You cannot integrate that with a Riemann integral. You can't even attempt to find the area under that. It's not a curve because it's discontinuous everywhere. But you can calculate the Lebesgue integral of that thing. It's this approach that allowed us to start to understand real numbers better. So, for example, when I say that there's more real numbers than there are fractions, right, that the reals are in some sense strictly larger than the rationals, this Lebesgue approach is going to allow us to understand that. The integral of that Dirichlet function is 0, which means like all the weight of that function is down along the line y equals 0. It's like a faint sprinkling of dust along the line y equals 1, and then a quite heavy line, in fact, a more or less solid line along y equals 0. It's very, very weird. There's a lot of deeply counterintuitive stuff here. But the approach we're going to take is going to be very straightforward. We will take a function, and it will be a continuous function for us, at least most of the time, or have finitely many discontinuities. You will chop up its domain and make a shitload of rectangles. And eventually I'll give you a formula that allows you to skip making all the rectangles involving an antiderivative. But for now, this is all I want to say, is that there's the game moving forwards is finding areas. At least that's where we begin, just like finding tangent lines is where we begin with differential calculus. And that the way we're going to do it is the way pioneered by Newton, Leibniz, and Riemann, which involves some rectangles being drawn in vertically. This is going to require the use of sigma notation. So one last little comment here before we start on review problems. Chapter 5 will involve use of the capital sigma summation notation. And I say this so that after Wednesday, don't burn any time on this yet, but after Wednesday, I want you guys to go back and make sure you know how to calculate something like this, or this, or this. The first one, the way this works is the capital sigma stands for the word sum, as in SUM, as in to add up. So we're going to add up numbers of the form 1 over k as k runs from 1 to 5. So the first number of the form 1 over k as k runs from 1 to 5 is 1 over 1. And we're going to add that to 1 over 2. And we're going to add that to 1 over 3. And we're going to add that to 1 over 4. We're going to add that to 1 over 5. This is what the capital sigma symbol does mathematically. It says, take the stuff that's inside of me and add it up. And then the kind of range over which you will be adding those things are specified by this number at the bottom. So start at k equals 1 and end at k equals 5. So it says, add up all the numbers of the form 1 over k as k goes from 1 to 5. So that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. I'm not going to simplify this for you right now, and you won't need to do much of that, but you do need to know how to interpret this as this, and you need to know how to interpret this in this notation. So the next one would be add up all the numbers of the form I squared as I goes from 0 to 3. So that would be 0 squared plus 1 squared plus 2 squared plus 3 squared. And this last guy would be saying add up all the numbers of the form 2n plus 1 as n runs from 1 to 4. So this would be 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1 plus 2 times 4 plus 1. This sigma notation is the way we're going to describe adding up all of the areas of the rectangles, right? If I want to get this blue area by adding up the area of these rectangles, I will use the thing inside the sigma will be the area of one rectangle, and then I'll say I'm going to add all of those up. So this capital sigma operator is the most convenient way to describe adding up a bunch of things that all fit in a certain pattern. And the rectangles will all fit in a certain pattern because they're all going to be coming from the same function. All right, that's it. That's your intro to chapter 5. The sigma summation notation is something that's supposed to be taught in pre-calculus, at least here at Santa Fe. But I have had students in the past who didn't see it at all in pre-calc. My wife, for example, took pre-calculus with us, and I don't think she got any practice with the sigma operator there. So just wanted to let you know that's what's coming. And now we'll go over to the chat and we'll work some problems. So we want numbers 2 and 3 from the study guide, numbers 7 and 13 from the study guide. Feel free to look outside the study guide as well. But yeah, okay. So let's look at those in order. Yeah, it's sad. I think a lot of people probably, yep, yeah, neither Sarah nor Yiping got that in their pre-calc class. It's so sad. I'm really sorry that that happened to you guys. It shouldn't happen that way. Unfortunately, with the pandemic, standards have slipped. You know, people, not just students, professors too, are not doing what they should do. Okay. So number 2 on the study guide says use logarithmic differentiation to find the derivative of the function sine 5x all raised to the power of ln x. So let me first review what logarithmic differentiation is. Specifically for powers, if I have something like y equals f of x all raised to the g of x power, these are the things where we need logarithmic differentiation. Logarithmic differentiation can be useful for other things, but this is a case where we absolutely need it. So in order to differentiate something of this form, we must first take the natural log on both sides. Then differentiate implicitly. It's interesting. So it seems like most of us didn't get much exposure to this in college, maybe a little bit in high school. I can try to put a bit of a review together for you guys with that stuff. Just a fun word of warning. Here's what my Calc 2 students are doing right now. It's lots of stuff like that. Like this, right? It's all capital sigma stuff. So there's a healthy dose of it here, and there's a much bigger dose of it in Calc 2. All right. So to differentiate a function that is like some variable quantity raised to another variable quantity, the only way to do it is to take the natural log on both sides, because this is not a power function. It's not some variable raised to a constant power. And it's also not an exponential function. It's not some constant raised to a variable quantity. If both of these are variables, like in our problem here, sine 5x is variable, ln x is variable, then the only way to attack is logarithmically. So if y is equal to f of x all raised to the g of x, that means that the natural log of y would be the natural log of f of x to the g of x. Now, why on earth is taking a logarithm going to help? Can we simplify
It allows us to uncouple the power and turn it into multiplication.
Yeah, exactly. This power will cease to be a power. He will come down here. We have this rule that says, I'll write it with natural log. The natural log of a to the b is b times the natural log of a. It doesn't have to be the natural log. Any base log would work, but that's the one we like. So this is going to become g of x times the natural log of f of x. And so I could differentiate now using the product rule. The catch is you need to differentiate implicitly. So if I differentiate ln of y implicitly with respect to x, I get 1 over y times y prime, or y prime over y. You could write it that way also. And on the right-hand side, I use the product rule. I would get g prime times ln of f of x plus g of x times 1 over f of x times f primed of x by the chain rule. And then we can solve for y primed by multiplying both sides by y. Now, this is not a formula anybody should memorize. I'm not advocating for that. I'm just showing you how the pattern goes in general. So what is logarithmic differentiation? In general, logarithmic differentiation is where you take a natural log and then differentiate implicitly. Functions of the form f of x to the g of x require logarithmic differentiation. Other functions, like a big nasty product, a bunch of things multiplied together, encourage logarithmic differentiation because the log will turn that multiplication into addition. And it's much easier to differentiate a bunch of stuff added up than it is a bunch of stuff multiplied, because you don't need to use a million applications of the product rule. So logarithmic differentiation, if I ask you use logarithmic differentiation, what that means is take the log, then differentiate implicitly. So with that in mind, sine 5x all to the natural log of x. Let me change it a little bit. So let me say my y is going to be tangent of 2x all raised to the ln of x, something like that. I'll just change the sign to a tangent. So it says use logarithmic differentiation. That means I'm going to take the natural log and then differentiate implicitly. So this means that the natural log of y would be equal to the natural log of tan 2x raised to the ln x, which is ln x times the ln of tangent of 2x. Just algebra rules for logarithms. You'll never need to exponentiate to recover the answer here. This isn't like those L'Hopital rule problems, because when we differentiate on the left, the log will go away. So just remember, you're differentiating on both sides implicitly with respect to x, which means the logarithm on the left will go away. And in order to solve for y prime, you just need to multiply both sides by y. So I see what you're asking, Yiping. It's kind of similar feeling to that limit problem where you had to take the ln on both sides and then use L'Hopital's rule. But here we're not taking a limit, we're taking a derivative. And when you take the derivative on the left-hand side, the ln will go away. And that means you don't need to exponentiate. You don't need to, put e, put both sides in the power of e. That is not necessary. So now we differentiate on both sides. On the left-hand side, I get y prime over y. I'll write it like that. This is because d dx of ln y is 1 over y times y prime, which is the same as y prime over y. I just like to write it as y prime over y. And on the right-hand side, I will differentiate using the product rule. So first I differentiate ln x, and I leave ln tan 2x alone. And then I add that to what I get when I leave the ln of x alone. And now I need to differentiate ln tangent of 2x. So downstairs, you'll get a tangent of 2x, right? The derivative of the outside, derivative of ln of some stuff is 1 over that stuff. And then you multiply by the derivative of the inside. Well, the derivative of tangent 2x, that's a chain rule thing. That's secant squared of 2x times 2. So this is what we get after differentiating on both sides. There's probably some cleaning up I can do here because I've got a secant squared of 2x divided by a tangent of 2x. But I would just finish the problem here if we're not told to do anything else with it by writing this as the natural log of tan 2x over x plus 2 ln x secant squared x over tangent of 2x all times y. And then you plug back in for y. So this would be ln of the tangent of 2x divided by x plus 2 times the natural log of x times secant squared x divided by the tangent of 2x times y, which is tan 2x all raised to the ln of x. So this would be my final answer. Any questions on the specific steps here? Why any of those derivatives came out the way they did, stuff like that? Okay. Now, God forbid you have to find something like horizontal tangent lines for this, because setting this to 0 is going to be a nightmare. But, I could ask you for the slope at x equals pi over 6 or something, and then you could crunch that out. How did I pull the tangent out of the last part? Are we talking about this piece? So I'm not factoring there. That's sneaky, right? I had y prime over y equals all this stuff, and then I multiplied over by y, and then I plugged in. So y is tangent 2x raised to the ln x. Yeah, factoring a tangent 2x out of this is not possible. Definitely not a tangent 2x to the ln x. So we're just plugging this in. This would be what we call an implicit derivative, because it involves both the x stuff and the y stuff. This would be an explicit form for the derivative. And if the question didn't say give an explicit form, then I would accept this as an answer also. Okay. Other places where logarithmic differentiation is useful. Would be stuff like y equals, I don't know, the square root of sine 5x over x cubed tangent 2x times like x squared minus 1, something like this. Right, where you've got a big nasty mess of things all raised to powers, multiplied and divided, because the natural log of this thing is much nicer than the thing itself. Right, differentiating this would be a nightmare if you jump in right away. But if you take the natural log first, then the power comes down, the division becomes subtraction, and all the multiplication becomes addition. Oh, yeah, so I mentioned setting this to 0 would be very hard, but plugging in pi over 6 for x would be relatively easy. Well, because if you plug an x value in here, then you just plug it in. And even if you're in a nasty situation, like what is the natural log of pi over 6? I don't know. You can still write it down. All right. If I asked you for the slope of the tangent line at x equals pi over 6, you could plug pi over 6 in here, And even as scary as the thing may look, you can still write it down. But if I ask you, where is this equal to 0, then that's a very hard equation to solve. You would have to set it equal to 0 and try to solve for x, which is, I think, impossible, certainly by hand. Okay, other stuff from the study guide, we wanted to see number 3, right? So a fellow starts walking north at 4 feet per second from a point P. 5 minutes later, a lady starts walking south at 5 feet per second from a point 500 feet due east of P. At what rate are the people moving apart 15 minutes later? Now, this does sound a little bit complicated. So first I'll say this, let's put P at the origin. Simplifying assumption. You could pick this problem up and shift it around, and it will have no effect on their relative positions. So let me put P at the origin. I'll write this down first. So let's do that. Move this over without it. No. Okay. So man starts walking north. 4 feet per second. 5 minutes later, the woman starts walking south. At 5 feet per second. Starting 500 feet east. Of P. That's from P. At what rate are they moving apart 15 minutes after the woman starts walking? Okay. So I've just written down the crucial stuff here. Like I said, let's put P at the origin. So wherever the point P is, it really doesn't matter. All that matters is their relative position. So I'll assume P is here. The fella starts at P and he's going to walk north at 4 feet per second. So the fellow is walking like this. He's going north and he's going at 4 feet per second. The woman is going to start 500 feet east of P. So that would be over here. I'll call this 500. And she's going to walk due south at 5 feet per second. So the position of the man, let me call that 0, y. And the position of the woman, I can't use y here. Let's call it 0, w. Whatever. Now the catch is that she starts after him, right? She starts 15 minutes after he starts. So what we want to do is find a formula for the distance between them, right? That's the thing we're trying to determine. So the distance from the one point to the other point, and let me again call it L to avoid running into the issue with using D to mean multiple things. I can actually find an explicit formula for both of these points. And that's one way to approach this. So can we find a formula for the function y if he starts at time t equals 0? So if the man, well, first let me write down L.
Pythagorean theorem.
Yeah. So L squared is what? I can think of that as making up a little right triangle like this. L squared would be this squared plus this squared. So that's y minus w, or if we're thinking in terms of distances here, so we think of w as being negative, we have to be a little bit careful. Yeah, if I'm calling this point 0, w, then this would be y minus w squared plus this distance, which is 500 squared. So again, I'm thinking of this point as the ordered pair 0, w. I'm not saying w is this distance, right? W would be the negative of this distance because we're going down. And here, this point would be 0, y, where y is positive. So the vertical distance here is y, and the vertical distance here is w. But if you're thinking of w as being negative, then this would be y minus w. All right. One option is to try and find an explicit formula for both y and w. But I think smarter than that would be to just go ahead and differentiate on both sides and see what we need. So remember, with these problems, we always want to ask, what do I want? I want dl dt 15 minutes after the woman starts walking, which is how long after the man starts walking? Well, she starts walking 5 minutes after he does, right? So that would be 20 minutes after the man sets off. We want that. What do we know? I know that dy dt is the speed the man is walking. He's walking north, so this y would be increasing. He's walking north at 4 feet per second. I'll just say 4. And that dw dt, she's walking south, so that this coordinate w, this point is going down, so dw dt would be negative 5. And that's true for all times t. So the fact that the woman
Can I set W is positive number so that I don't need to use the negative to count this equation so that I will not confuse?
It's up to you. It's up to you. So I like working in coordinates. I like saying that like this is the y-axis and this is the x-axis, and that means that this w has to be negative. But if you wanted to think of this distance as L or as y plus w, then you could think of dw dt as being positive 5. And this would be y plus w instead of y minus w. That would work okay. So if you want to use this as positive, then you change this minus to a plus. As long as you do both of those things, you'll be okay. So what I would do now is differentiate on both sides implicitly with respect to time. And I'm going to write this out in the operator notation. so. I think it's nice to remind ourselves that we're differentiating with respect to time. So the time derivative of L squared would be 2L times dl dt. And the time derivative of y minus w squared would be 2 times y minus w times, ooh, this is a little wonky. It would be the derivative of the inside here, which is dy dt minus dw dt. And then the 500 squared differentiates to 0. Another option, you could FOIL this out. This is y squared minus 2yw plus w squared. And then you could differentiate that instead. You'll get the same thing. All right. So I get 2L dl dt equals 2 times y minus w times dy dt minus dw dt. I can divide both sides by 2. And I get L times dl dt equals y minus w times dy dt minus dw dt. We want dl dt. We know dy dt and dw dt. In addition to those things, in order to solve for dl dt, I will need to know at that moment what is L, and at that moment what is y minus w. So for all time, after the woman starts walking, dy dt is equal to 4, and dw dt is equal to -5. So I can plug those things in, and I arrive at L times dl dt equals y minus w times dy dt, which is 4, minus dw dt, which is minus -5. So this is 4 minus -5 is 9. So to finish my problem now and solve for dl dt, I need to know at the moment in question, right? 15 minutes after the woman sets off or 20 minutes after the man sets off, I need to know what is L, what is Y, and what is W. And to that end, I suggest redrawing the picture. So at the moment in question, where is everybody? My woman is down here somewhere. We'll figure out exactly where at this point. And my man is up here somewhere. So how long has the man been walking? 20 minutes, right?
Yeah.
And he's walking at 4 feet per second. So how far has he gone?
4 times 20 times, sorry, 4 times 15 times 60.
Man has been walking for 20 minutes at 4 feet per second. So y, the distance he's gone is equal to the speed he's going at times the distance equals rate times time, right? So the speed or rate times the time. Now the catch is you can either do this in feet per second or feet per minute. You're gonna have to either convert these minutes to seconds or these seconds to minutes. It's up to you. Which would you guys like to do? how do we want our answer?
This 20 minutes is the man's walking about 4 feet per second in 20 minutes, and then after that the lady is beginning to walk. Or this 20 minutes is include of the lady's walk time.
So for the first 5 minutes of the man's walking, the lady is standing still, but the man has been walking for 20 minutes. Yeah. So remember the question said, how fast are they moving apart? 15 minutes after the woman starts walking. So how long is that after the man starts walking? Well, the man started walking right away. And then 5 minutes later, the woman started walking. So if the woman's been walking for 15 minutes, then the man has been walking for 20. So I'm going to use the 15 minutes when I calculate the distance the woman has gone. I'm going to turn everything into seconds, because I think since our velocities were given to us in feet per second, we should give the answer in feet per second. So 20 minutes is how many seconds?
Can I assume the man start walking after 5 minutes and the speed is 4 feet per second plus the lady's speed, and I count time again. Their total speed and multiple 20 minutes.
I would be a little
Can't do
bit
that.
careful about it. So I'm going through this in a very particular way because it's easy to make incorrect assumptions. Remember, the man started walking first, so he's been walking longer. If you try to see if I'm understanding correctly.
If the man beginning walk 5 minutes, so I just use his speed multiple 5 minutes and then get the distance
I don't
in
think that's
5
correct.
minutes.
So if the man hasn't been walking for 5 minutes though. At the moment the woman starts walking, the man has already been walking for 5 minutes. But the man has been walking for a total of 20 minutes. So he sets off first, right? And he's walking this whole time. But the lady is just sitting here for 5 minutes. She doesn't start until he's already been walking for 5 minutes.
So the man's speed is 5 feet per second. So I use the 5 minutes transfer to the seconds, total 5 minutes in second. I transfer to that and multiple 5 feet per second, and I get the distance for the man in 5 minutes. And then I assume the man stopped walking, and I use the ladies. Maybe after that, the ladies beginning to walk is 20 minutes minus 5 minutes, so it's 15 minutes. After 15 minutes, I use the man and the ladies, their speed together is 4 feet plus 5 feet is equal to 9 feet. And I use 15 minutes multiple 9 feet per second.
Something like that might work. Yeah, that's one way of thinking of this, where you kind of combine them into a single thing. You just have to be very careful about how you do it. So if they both set off at the same time, then it would be very easy to combine this kind of thing into one standing here and this sort of thing. So you could say that the man walks for 5 minutes, and then when the woman starts walking, it's the same thing as one of them holding still and the other one walking. But because of the geometry of the situation, I think it might not come out exactly the same. So let's see if you get the same thing I get here. First, let me finish this calculation.
Okay,
so,
thanks.
After 20 minutes, the man has traveled how far? Well, he's been walking at 4 feet per second this whole time, and he's been doing it for 20 minutes. 20 minutes in seconds is 20 times 60, because there's 60 seconds in a minute. So this is 1,200 times 4, which is, let me just write it, 1,200, get it out of my head, times 4. And then 12 times 4 is 48. So this is 4,800 feet. The man has walked 4,800 feet, And the woman she's been walking for 15 minutes at 5 feet per second. So W here, and again, being careful, W is negative. This would be negative time times the speed. So 15 times 60 is how many seconds she's been walking. And her speed is 5. And it's like a velocity, she's going down. So the negative times negative would make positive here. 15 times 60, what is that? Well, 15 times 6 is, it's just so bad. 900. This is 900 times 5. Oh, sorry. 4,500. So she has gone 4,500 feet. The nice thing about setting it up the way that I've set it up here is that you don't need to think too carefully about the woman starting first or the man starting first. It doesn't really matter. This relationship is always true. And when you take the derivatives, you get a relationship that is always true. And then we just think about the bits that we need. The dy dt minus dw dt, that's 9. And then y minus w and L are the only two things we need in order to calculate dl dt. So L here is going to be the distance in this picture. And that distance I can calculate from these. I've got W and I've got Y. They are 4,500 and 4,800 respectively. Let's see. Oh, let me see. I'm sorry. I think my W coordinate should be negative. I built a negative in there that I shouldn't have. So this guy is going to be Y minus W, which is 4,800 minus negative 4,500. The 9 is still 9. And over here, L will need to calculate that at that moment. I'll do this down here. Again, I'll set up L squared equals Y minus W squared plus 500 squared. So at that moment, that is 4,800 plus 4,500, which is, we'll just write it out. Plus 500 squared. So that would be 8,000 plus 1,300 is 9,300 plus 500 squared. So what is this? $9,300 86,000. Sorry, 86,490,000. 86,490,000 plus 500 squared. It's 250,000. And if I add these things, I get this, and I would like to take the square root of that. So I get 9,313.43. Did they specify a level of precision? Round to 2 decimal places. So at this step, I'll give myself like 4 decimal places of accuracy because we still have to plug in and do some further arithmetic. It's nice. So L is approximately 9,313 0.43116. How about that? 116, and then the next sig fig is a 1, so this is pretty good. So that's the value of L that I'm going to plug in here. L times dl dt equals that. There. I'll take my 9313.43116 dl dt equals 4,800 plus 4,500, we said was 9,300 times 9. And we can crunch this out. $9,300 times 9. $83,700. And then we divide that by 9313. For 3116, and we get about 8.987. Which is about 8.987. All right, so this would be dl dt. That is how fast they are moving apart at that moment. Nice, right? So the trick is in the setup. The trick is in figuring out how you want to describe the problem mathematically. And for me, someone who really likes having a good picture, the first thing I do is draw the coordinates, right? Place P at the origin, and then figure out where everybody is going. If the woman is 500 feet due east, then she's starting at the point 500, 0. And oh, I'm sorry, it's 500, 0, not 0, W. But giving yourself some coordinates is the nice start. Yeah. This doesn't have any effect on us. This is 500, W, sorry. Give yourself some coordinates, draw the picture, write down what you want and what you know. Use the picture to set up the necessary geometry. So this is a right triangle. I know this distance is y minus w. I know that this distance is 500. So this guy would satisfy this Pythagorean relation. Once you get here, you're in good shape. You can differentiate on both sides. The derivative is not too bad. And then you arrive here. And once you get to this place, you look back at what you know this. And you look at what you have left after you plug that in. Generally, after you've plugged in the information that you have, you'll still need to solve for some other stuff. You've probably noticed that pattern in these related rates problems. Generally, those things that you need to solve for are particular values of the variables that you're working with. So it's useful to redraw the picture and then figure out at the moment in question, what is L? At the moment in question, what is Y? And at the moment in question, what is W? Now, the way I chose to do this was just by following exactly what they said, that the man starts walking immediately and the woman starts walking 5 minutes later. So the man's walking for a total of 20 minutes, and that makes it easy for me to calculate how far he went. And the woman's been walking for a total of 15 minutes. That makes it easy for me to calculate how far she went. And I don't need to stress about combining them into a single vector. But the thing that Yiping was describing there, where you kind of think of one of them as standing still and the other one as moving, can also be done. You're changing the reference frame. But for me, it's really helpful to have a fixed reference frame. It just makes things easier to think about. So putting my point where I start at the origin and then letting them do their thing is really helpful for me. But if you have a more powerful brain for physics than I do, I've always struggled with physics. I find mathematics very intuitive, but physics very hard. This is how I choose to think about it. I'm curious, Yiping, did you get the same thing I got?
Yes.
Cool, nicely done, nicely done. All right, I think we do have time for one more. Is there another problem that you guys wanted to see? Oh, let's see, 7 and 13, right? So I don't think we'll have time for both, but we should be able to look at least one of them. So 7, find the absolute min and absolute max. And 13, use L'Hopital's rule to calculate this limit. So L'Hopital's rule is necessary here. There's not a more elementary method. I'll set up 13 for you, and then we'll go back and do 7. I don't have a problem with going a little bit over today. That's all right. So I want to find lim x to 0 plus 3x plus 1 raised to the cotangent of x power. Let me say, let f of x be that function, 3x plus 1 raised to the cotangent of x. And we want the limit as x goes to 0 plus of f of x. I'm going to work with the natural log of f of x. So I'll be taking the limit as x goes to 0 plus of that instead. As x goes to 0, cotangent is, let's see, that's cosine over sine. He's blowing up to infinity, and this is going to 1. So this looks like 1 to the infinity, which is an indeterminate form. So this is lim x to 0 plus the natural log of 3x plus 1 raised to the power cotangent x, which is lim x to 0 plus cotangent x times the natural log of 3x plus 1. Now, as x goes to 0, this looks like the cotangent function blows up to infinity at 0, right? Because cosine of 0 is 1 and sine of 0 is 0. The natural log of 1 is 0. So this looks like infinity times 0, which is an indeterminate product. So one of them has to go downstairs. Now, I don't know about you, I like tangent more than cotangent. So I would shove the cotangent downstairs. I'd rather differentiate tangent than the reciprocal of that log. So I would write this as the natural log of 3x plus 1 divided by the reciprocal of cotangent, which is tangent. So just algebra here. Now, as x goes to 0 plus, we're getting a 0 upstairs and tangent of 0 downstairs. This is an indeterminate ratio. So you'll apply L'Hopital's rule at this stage. We got lim x to 0 plus 3 over 3x plus 1 upstairs and secant squared of x downstairs. The derivative of the natural log of 3x plus 1 is 1 divided by 3x plus 1 times the derivative of 3x plus 1, which is just 3. So this is the derivative of the top. The derivative of tangent x is just secant squared x. And both of these are now defined and continuous, in fact, at 0. As I send x to 0 here, my numerator becomes 3 over 1. And my denominator is secant squared of 0. What is secant squared of 0?
One.
Yeah, 1. So this is 1 squared downstairs. So this is 3. Am I done?
You have to exponentiate now.
Good. So the difference between kind of these problems and the logarithmic differentiation problems, here I'm taking a limit, not a derivative. So the ln doesn't go away with the limit. So since lim x to 0 plus ln of f of x is equal to 3, the lim x to 0 plus of f of x itself must be e to the 3. And that's our answer. All right.
Is it a L'Hospital rule only used for the horizontal asymptote?
Not necessarily. Here, what we're doing, we're using L'Hopital's rule to look at this function near 0. So that's definitely not a horizontal asymptote. And the concern is that it might have been a vertical asymptote, but it's neither of those things.
So if the graph has vertical asymptote, I can use the L'Hospital rule to look at the behavior nearby the vertical asymptote.
Yeah, you can use L'Hopital's rule anywhere that you have, sorry, where are we here? I'm going to try to this 0, p cubed. I don't know what to do there. So here what we did is we used L'Hopital's rule to kind of find a y-intercept. Strange, right? But you can use L'Hopital's rule anywhere you're using a limit that looks like an indeterminate form. So here what we had was a limit that gave us an indeterminate power. And so L'Hopital's rule is useful. It can also show up when you're looking for vertical asymptotes or horizontal asymptotes. Those are a little bit more common because specifically horizontal asymptotes, that's where you'll see it a lot, right? L'Hopital's rule shows up a lot with horizontal asymptotes, but not exclusively. And the general trigger for L'Hopital's rule is if you have an indeterminate form that you cannot figure out some other way. So anytime you're taking a limit where you get an indeterminate form and you don't see an algebra process that will let you simplify, then you will need L'Hopital's rule. In the curve sketching section, that's usually going to mean horizontal asymptotes, but not always. Okay, the other one we wanted to see was number 7, which was a finding extrema problem. So we want to find the absolute min and max for this function on that closed bounded interval. And we can use the closed interval method for this. F of x is 5t plus the cotangent of t over 2. And we're looking on the closed bounded interval from pi over 4 to 7 pi over 4. And we're going to get there via the closed interval method. And remember what the closed interval method says? It says find any critical numbers and then compare the function value at those critical numbers to the function value at the endpoints. That's it. So the absolute min and absolute max must come from either a critical number or one of the endpoints. Let's look at the endpoints first, just to get them out of the way. F of pi over 4, I think A is pi over 4, is 5 times pi over 4 plus the cotangent of pi over 4 divided by 2. Ooh, that's a nasty number. So this is 5 pi over 4 plus the cotangent of pi over 8. Now the cotangent of pi over 8 is not a nice number. It's not a number we know from our unit circle, and if you're going to find it exactly, you would have to use a half angle identity for the cotangent function. So I will approximate this. .4-ish. And if we add 5 pi over 4 to that, this is about 6.3, 6.34. F of B is f of 7 pi over 4, which is 5 times 7 pi over 4, plus the cotangent of 7 pi over 4 divided by 2, which is, oh, sorry, 5 times 7 is 35. So this is 35 pi over 4 plus the cotangent of 7 pi over 8. And again, I'll just approximate, so we have a rough size estimate. 7 pi over 8 and 35 pi over 4. It's about 25.07. And these rough decimal approximations you could get using the TI-30, just using a basic calculator. The problems on the test, I'll make sure that you wouldn't need to calculate something like the cotangent of pi over 8 for. So you can do it without a calculator if you want. Critical numbers then come from f primed being 0 or undefined. So let's find what f primed is. F primed is 5 plus, right, derivative of 5t is 5. I'm sorry, t. The derivative of cotangent is negative cosecant squared. So this would be minus cosecant squared of t over 2. And then by the chain rule, you have to multiply by the derivative of t over 2, which is 1/2. So altogether, that derivative is 5 minus 1/2 cosecant squared of t over 2. And we want to know, where is this equal to 0 and where is this undefined? F prime of t will be equal to 0 if and only if 5 minus 1/2 cosecant squared t over 2 is equal to 0, which would mean 5 is equal to 1/2 cosecant squared t over 2, or 10 is equal to cosecant squared of t over 2. And this is also a little bit nasty. Goodness, yeah, this is pretty brutal. So what could we do with the cosecant squared of t over 2? We can write it as 1 over sine squared t over 2 and use some trig identities. This would be my advice. So remember, cosecant theta is 1 over the sine of theta. I really do want the exact values here, so this isn't something I'm going to do with a calculator. So this is the same as saying 10 equals 1 over sine squared of t over 2. And then there is an identity that says, let me see, there's a few different flavors of this. Sine squared of theta is the same as 1/2 times 1 minus cos 2 theta, which means sine squared of t over 2 would be equal to 1/2 times 1 minus cosine of t. These are sometimes called half-angle identities. I usually remember them like this, but I think in trigonometry, they teach it as sine of t over 2 equals the square root of all this stuff. This is the definition here, and this is the half-angle identity. So what do I have here? I have 10 equals 1 divided by 1/2 times 1 minus cosine t. Nasty. All right. We can multiply. Let's just clean it up. So this is the same as saying 10 equals 2 over 1 minus cos t. All right, the 1/2 downstairs is the same as a 2 upstairs. Then we can divide both sides by 2. We're back to 5 equals 1 over 1 minus cos t. This isn't going to be nice. And then we'll have 5 times 1 minus cos t equals 1. I can distribute the 5. And then, maybe it won't be too bad. Subtracting that 5 over, I get negative 5 cos t equals 1 minus 5, which is 4, negative 4. So cos t is 4/5. Yep, and this is not a nice number. So unfortunately, we are going to need some amount of approximation, which means we could have worked from here instead of rewriting it like this, but it's a matter of taste. So if the cosine of t is 4 over 5, then t would have to be the inverse, one solution would be the inverse cosine of 4/5. And this is not a nice number in radians. It's not a nice number in degrees either. 0.6435 radians. And we're working from pi over 4 to 7 pi over 4. We have to ask ourselves, is this bigger than pi over 4? Well, pi is about 3, so pi over 4 is smaller than 1. 7 pi over 4. Let's see. This is an unpleasant problem. It's not bigger than pi over 4. So let me take a quick look here. Let's look at this graph. Can I write something down? And we want to restrict from pi over 4. Kind of seems, yeah, so that min, right? Take a look at that. Here we go. Let me copy paste this down below. So the min we just found was this guy. Oh, no, not him. Just to the left of him here. This is the one I just found, right? 0.6435. That's that approximation. But pi over 4, that left endpoint for my problem, is not in that interval. So this is kind of one of those irritating things. This is not in the interval pi over 4 to 7 pi over 4. So my only critical number, and the function is periodic. We could find more of these by extending periodically. But since the period of cotangent is pi, if we add pi to this, we're going to stay outside this interval. There are no critical numbers. in this interval, which means your min and your max are going to come from the endpoints. This is a bad problem. Did I write something down wrong? 5 cotangent. Oh my God, I'm so fucking stupid. I'm sorry, guys. I left this 5 off. Yeah, so we were supposed to work with 5t plus 5 cotangent t over 2. I just wrote cotangent of t over 2. All right. I know we've gone over time here, but my office hour doesn't start until 1, and I hate to leave it on that note. So let me run you through this properly really quick. Should have noticed that sooner. We want to add min max on pi over 4 to 7 pi over 4. So again, f of pi over 4 and f of 7 pi over 4, these are nasty numbers. This is 5 pi over 4 plus 5 times the cotangent of pi over 8. And we will need to approximate that. F of 7 pi over 4 is 35 pi over 4 plus 5 times the cotangent of 7 pi over 8. And these, I knew something. Should have known something. All right, so this is about 15.99. And 8, I guess. And the other one is 35 pi over 4 plus 5 cotangent 7 pi over 8, 15.41. Ooh, very close. Really? Yeah, okay. Very close. All right, 15.418. So those are our endpoints, and then f primed here. Not as bad as I thought it was with that last one. This will be 5 plus 5 times negative cosecant squared t over 2 times 1/2, which is 5 minus 5 halves cosecant squared t over 2. So f primed equals 0 if and only if 5 minus 5 halves cosecant squared t over 2 equals 0, which means negative 5 halves cosecant squared t over 2 is equal to negative 5. Yeah, and this will be a nice value. So here we get cosecant squared of t over 2. If you divide both sides by negative 5, this becomes a 1, and then multiply both sides by 2, you get a 2. So this means that cosecant, so regular cosecant of t over 2 would be plus or minus the square root of 2. So we want to ask ourselves, where is the cosecant function equal to positive or negative root 2? Remember, cosecant is the reciprocal of sine. So we're looking for places where sine is root 2 over 2, i.e. the sine of t over 2 would be plus or minus square root of 2 over 2. So there's 4 such places. They're all the multiples of pi over 4, all right? This is true at any, at t over 2 at t over 2 equals any multiple of pi over 4. So the sine function is equal to root 2 over 2. Anytime it's inside is any of these multiples of pi over 4, right? Which is this guy, this guy, this guy, and this guy. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. I guess technically any odd multiple of pi over 4. Now, which one of those would come from my interval? This would mean t over 2 equals pi over 4. T over 2 equals 3 pi over 4. T over 2 equals 5 pi over 4. Or t over 2 equals 7 pi over 4. That's all of them from 0 to 2 pi. And then
The last two are out.
yeah, so this would, well, so this would mean that t, we got to multiply both sides by 2. So this would mean t is pi over 2. This would mean t is 3 pi over 2. This would mean t is 5 pi over 2. And this would mean that t is 7 pi over 2. So I think maybe even more than that. 7 pi over 4 is, let's see, 7 pi over 4 is here. So we're looking for stuff that's between positive pi over 4 and 7 pi over 4. That means our t value has to be somewhere in here. So what is that? Pi over 2 is good. 3 pi over 2 is good. Yeah, 5 pi over 2 and 7 pi over 2 are no good. These are outside our interval. So you're exactly right, Sarah. We just stick with the first two. Those are our critical numbers from f prime equals 0. We also want to be wary of anywhere f prime is undefined. And that would be anywhere that this cosecant squared is undefined, which would be anywhere sine is 0. So we got to make sure that we stay away from 0. All right, specific t over 2 equals 0. We also have to stay away from t over 2 equals pi, which would mean 4 pi. Yeah, we're good. Right here, this is t over 2, that would mean t is itself 0. The next one would be t over 2 equals 2 pi, which would mean t is 4 pi. All of these are outside the interval. So here, I thought this would be a quick problem. All right. So the only things that remain to be seen are the value of the function at pi over 2 and at 3 pi over 2. So let me come up here. We're going to compare these to f of pi over 2 and f of, what did I say, 3 pi over 2? Yeah. So this would be 5 pi over 2 plus 5 times the cotangent of pi over 2 divided by 2 is pi over 4. And this would be 5 times 3 pi over 2 is 15 pi over 2 plus 5 times the cotangent of 3 pi over 2 divided by 2, which is 3 pi over 4. And these we can calculate exactly if we want. This is 5 pi over 2 plus the cotangent of pi over 4 is what?
One.
1, yeah. This is 5 pi over 2 plus 5 times 1, or plus 5. What about the cotangent of 3 pi over 4? So I've got my 15 pi over 2.
Negative 1?
Yeah, cotangent of 3 pi over 4 is -1. So this is -5. And then we can approximate each of these. So I've got 5 pi over 2 plus 5, which is 12.854. And 15 pi over 2 minus 5, which is 18.562. Oh, so absolute min and absolute max. What's the largest of all these? F of 3 pi over 2. What's the smallest of all these? F of pi over 2 itself. So this guy, so the absolute min is 12, well, I'll say it's F of pi over 2, which is approximately 12.854. And the absolute max is F of 3 pi over 4, which is approximately 18.562. All right, very sorry about that. Failing to write the question down correct. Let's make it a teachable moment, right? On the test, you don't want to make the mistake I made the first time we ran through this, where I wrote down the function without this 5. Read the question carefully and make sure you write things down correctly, lest you go through that sort of hell and not realize it. Once we had the right function written down, this wasn't that bad. We did have to solve a trig equation, but the trig equation was not nearly as bad as the one that we looked at with the incorrect function. So here, taking our derivative and setting it equal to 0, we found that cosecant of t over 2 had to be plus or minus the square root of 2, which means that the sine of t over 2 is the reciprocal of this number. 1 over root 2 is just another way of writing root 2 over 2. So we had to find where sine is equal to positive or negative root 2 over 2. The inside of the sine function is t over 2. So it's going to be t over 2 equals those values. And then we solve each of them for t, identify the ones that are in our interval and the ones that are out of our interval. There are some places where this derivative is undefined as well, but none of them are in this interval. So then to finish things up, we just had to compare the function values at the two critical numbers to the function values at the end point. And in conclusion, let me show us this graph. And look at the restricted version. Here we are. So the blue is the thing we're actually working with. It's a portion of the red. At the endpoints, the function values are quite close, 15.9-ish, 15.4-ish. And then we do have mins and maxes at pi over 2 and 3 pi over 2. The min is about 12.584. And the max is about 18.562. And we found those where they should have been. So we're Gucci. All right. I'm sorry for making that look scary that first run through. That was my fault. I wrote the thing down wrong. Don't make that mistake on the test. That's it. So I am going to do an office hour today from 1 to 2. If you guys have other questions you want to talk about, you can bring them there. It's like they captured it right before it went insane. Yeah, true story. True story, right? This function is mighty odd. The cotangent function has a lot of asymptotes, and that 5t, if you look along the line, y equals 5t, that's kind of like what's going on here. So it's like someone took the cotangent function and kind of skewed it to go along that line. Yep, nifty stuff. Alrighty, gang, I'm going to sign out. I will see you guys either in office hours today or for the test on Wednesday. Remember, if you're taking the test at the testing center, be sure you've got a few hours to spare there because you might have to wait a little bit before you get started. But that's it. Otherwise, come in here to take the test with me. Make sure you sign into Zoom from your phone.
Professor John,
Yes.
your videos on the 29th, October 29th, is a wrong video. You put 1140.
Oh, okay. Let me take a look here. I'll bring that up so I can fix it. Oh, this one?
Yes.
Okay. Yeah, let me fix that for you. Sorry about that. Oh yeah, I see. Okay. Yeah, I'll take care of this. Thank you.
Thank you.
Of course.